Which alkane has the highest boiling point? A. CH3 CH2 CH3. B. CH3 3 C CH CH3 2. C. CH3 CH2 3 CH CH3 2. Or D. CH3 2 CH CH2 CH CH3 2. Let's start by drawing the formulae for the alkanes we're given in the question. For A, this is heptane, so drawing it skeletally, we would draw 7 carbons or a 7 carbon length chain. For B, we have branched chains, so we would have 3 CH3 groups attached to a carbon with just a hydrogen, and then 2 more CH3 groups attached. This is B, and this is A. Then for C, we have a straight chain for most except the end. So we have our CH3 attached to our CH2, another CH2, and then we're going to have our CH3s coming off the side. So this is C. And then for D, we would have mostly a straight chain, but we have 2 CH3 groups that make our CHs here, because these CHs are these carbons on our skeletal diagram. Now we're asked for the highest boiling point, so that's going to be the alkane with the fewest number of branched chains, and the alkane with the fewest number of branched chains is A. So we write A in the answer box provided. To get the mark for this question, you must write A in the box. Butane reacts with chlorine in the presence of ultraviolet radiation to form a mixture of organic products. Which equation shows a propagation step in the mechanism for this reaction? A. Cl2 makes 2 Cl radicals. B. A Cl radical and a C4H8Cl radical make C4H8Cl2. C. C4H9Cl and a Cl radical make C4H8Cl2 and a hydrogen radical. D. A Cl radical and C4H9Cl make C4H8Cl as a radical and HCl. This question is asking about free radical substitution and the steps in its mechanism. The equation we're given for A is known as an initiation step, and it's where radicals are made for the mechanism. So we can eliminate A as our possible answer. Then looking at the equation for B, this equation is a termination step, and it's where 2 radicals combine to make a single organic product. So we can also eliminate B from our possible answers. Now we're left with C and D. Both C and D involve a radical and an organic compound, and they're forming an organic product and a radical. However, looking at C, we're producing a hydrogen radical, and that is very unlikely in free radical substitution. It's much more likely that you would form hydrochloric acid, or HCl, and C4H8Cl as a radical, which would then continue in your second propagation step, where this radical would then react with chlorine. So we can eliminate C, as it's very unlikely we're going to form a hydrogen radical, and much more common, much more predictable that we're going to end up with hydrochloric acid and C4H8Cl as our radical in our propagation step. So we then write D in the answer box that we're given. To get the mark for this question, you must write D in the answer box provided. What is the name of the compound below? A. 3-propyl-pent-2-ene. B. 3-propyl-pent-3-ene. C. 3-ethyl-hex-2-ene. Or D. 4-ethyl-hex-4-ene. The first thing we need to do with this question is number the longest carbon chain. So if we number the longest carbon chain, we have 1, 2, 3, 4, 5, 6 carbons in our longest carbon chain. That means we're going to have hex as our prefix. So we can eliminate our answers with pent because it's not 5, it's 6. Then we need to look at where our highest priority groups are and how close they are to the different carbons. So we've numbered it correctly here because the double bond is the closest to carbon number 1. We want it to be the smallest number, not the biggest number. So here we've got it on carbon number 2. And then on carbon number 3, we have our ethyl group. That means our answer is C. So to get the mark for this question, we need to write C in the answer box provided. The structure of a stereoisomer is shown below. Which term correctly describes this stereoisomer? A. Cis. B. Trans. C. E. Or D. Z. So cis and trans isomers are to do with the placement of hydrogen around the double bond. There is not a single hydrogen around the double bond, so we can eliminate options A and B. Then we need to identify the highest priority group on the left and right of our double bond. So on the left, our highest priority group is the bottom left, our CH3-CH2 group, and then on the right, our highest priority group is our CH-CH3-2 group. So, as they're on opposite sides of the carbon-carbon double bond, that means that we have an E stereoisomer present. So, to get the mark for this question, we need to write C in the answer box provided. Which types of bonds are broken and formed in the reaction of ethene and bromine? A. A sigma bond is broken and a pi bond is formed. B. A pi bond is broken and a sigma bond is formed. C. A sigma and a pi bond are broken and a pi bond is formed. Or D. A sigma and a pi bond are broken and a sigma bond is formed. This question is asking about electrophilic addition because that is the mechanism between an alkene and a halogen, or a hydrogen halide. So if we start with ethene, when we draw it out, we've got C double bond and then we have 4 hydrogens attached either side of our double bond. And we're reacting with bromine. We're then going to form C in a single bond with 4 hydrogens and then 2 bromines attached because we're adding them to our ethene, hence the addition word in our mechanism. So if we look at the double bond, a double bond has a pi and a sigma bond. So the type of bond broken would either be C or D because they both have a pi and a sigma bond that we're told is broken. Then looking at the type of bond formed, a single bond is a sigma bond, which is D. So to get the mark for this question, we must write D in the answer box provided. What is the organic product of the reaction below? So what we're going to focus on is the OH-, which can be found in KOH. The OH- will act as our nucleophile. The OH- doesn't substitute on the benzene ring, and this is because benzene is electron dense and doesn't attract the nucleophile, so nucleophilic substitution can't occur on the benzene ring. So instead it's going to occur on the chlorine. So what we're looking for is nucleophilic substitution occurring on our CH2Cl group. Nucleophilic substitution is when an electron-rich nucleophile attracts a positively charged electrophile to replace a leaving group. So what we're going to do is we're going to replace the Cl on our side chain with an OH group. And the only product that we've been given in our options that shows this is A. So A is showing that the Cl is being replaced with an OH group. B does not show this, neither does C or D,
because B is showing that the OH group is being substituted onto the benzene ring, so is C, and so is D. Therefore, to get the mark for this question, you need to write A in the answer box provided.
What is the number of chiral carbon atoms in the steroid molecule below? A, 5, B, 6, C, 7, or D, 8? A chiral carbon is when you have 4 different functional groups attached to a carbon atom. So looking at this steroid molecule, if we work our way across from left to right, our first chiral carbon would be here. So we have 4 different groups attached. We have a hydrogen, we have this part of the steroid molecule, we have this part, and we have this carbon-carbon bond. Moving across, we have another chiral carbon here on our steroid molecule. Again, we have 4 different functional groups attached to this carbon atom. Similarly, moving on, we have a chiral carbon here and here. Also, there is one here with our CH3 group attached and one with our OH group attached. At each of these chiral carbons, there are 4 different functional groups attached to the carbon, and this is the definition that you will need to know if you're asked to define it later on in the exam. So looking at our options, we've given 5, 6, 7, and 8. Counting the number of chiral carbons here, we have 6. So that means our answer would be B. So to get the mark for this question, we must write B in the answer box provided. Phenol reacts with bromine. Which is the least likely organic product? So with this question, we're presented with 4 different organic products. Bromine, when reacting with phenol, has a 2,4,6 directing effect. So if we look at our options, A, we have a 2 and a 4, so A is a possible answer. So it is not the least likely organic product. Therefore, we can cross out A. For B, we have positions 2 and 6. So again, because it's a 2,4,6 directing effect, B is a possible organic product. So we can eliminate B. Looking at C, we have bromine at positions 2 and 3. 2 and 3 is not very likely, so it is extremely possible that C is our option as our least likely organic product. Finally, looking at D, just to confirm, well, the bromine is at 2, 4, and 6 on the positions of the phenol, and so it again is possible. Therefore, our answer has been confirmed that it's C, and to get the mark for this question, you must write C in the answer box provided. The repeat unit of a polymer is shown below. Which monomers could form this polymer? Firstly, let's look at the functional group of this polymer. So the functional group of this polymer is our ester link. That means we're going to need a dialcohol and a dicarboxylic acid to form our polyester. The alcohol we're looking for would be a 2-carbon chain with 4 hydrogens and then 2 alcohol groups either side. Looking at our options A to D, this structure of our dialcohol matches the option A alcohol. Then continuing, just to check that we have option A and that is correct, we need to look at our dicarboxylic acid. So we're looking for a dicarboxylic acid with a 4-carbon chain, 2 carboxylic acid groups on either end, 4 hydrogens, and if we compare to option A, well, it matches. We've got a 4-carbon chain with our 2 carboxylic acid groups on either end. So option A matches both our dialcohol and dicarboxylic acid. So to get the mark for this question, we must write A in the answer box provided. Which compound shows 4 peaks in its carbon-13 NMR spectrum? We're presented with 4 different organic compounds here. So firstly, we need to identify how many carbon-13 NMR peaks each compound would produce. So that means we need to look for lines of symmetry. If we look at compound A, our line of symmetry is here. And then we need to number the peaks in a carbon-13 NMR spectrum that we would expect. So we have 1 carbon environment here, 2, 3, 4, 5. So we've got 5 peaks in this carbon-13 NMR, and we're looking for something with 4 peaks. Therefore, we can eliminate A as a possible answer. Then looking at B, looking at the line of symmetry, we have a line of symmetry here. Now we need to number the peaks. So we would have 1 on both sides of the line of symmetry, 2, 3, 4. So B has 4 peaks in its carbon-13 NMR spectrum. So B is our answer, but just to clarify, let's check the others. So if we draw our lines of symmetry for C, we have 1, and then we need to number the carbon environment. So we would have 1, 2, 3, 4, 5. So C has 5, so it's not 4. We can eliminate C. Finally, checking that D is not our answer. We have 2 lines of symmetry across D, so we need to number its carbon environments. We have 1, 2, 3 carbon environments across D. So therefore, it's not our answer either. That means we've checked that B is our answer to this question. To get the mark for this question, you must write B in the answer box provided. A student reacts 4.50 grams of C6H5NH2 with excess CH3COCl in the reaction below. The reaction produces 3.25 grams of C6H5NHCOCH3. What is the percentage yield of C6H5NHCOCH3? A. 49.8, B. 68.9, C. 72.2, or D. 95.4. If we start by highlighting the key pieces of information in this question, our first key piece of information is the mass of C6H5NH2. Our second key piece of information is the mass produced of C6H5NHCOCH3. We're then going to use the equation triangle of mass divided by moles times the relative formula mass. We're going to work out moles, and we're going to use these moles to work out percentage yield. So firstly, working out the theoretical moles of C6H5NHCOCH3 that's produced, we would do 4.5 divided by 93, and that equals 0.04838 moles. And we have a 1-to-1 ratio of moles, so that means this is the theoretical moles of C6H5NHCOCH3 that we would expect to be produced. But the reaction says that 3.25 grams are produced, so we need to work out these moles. So that would be 3.25 divided by 135, and that equals 0.02407 moles. So we can already see that they're not the same. Now working out percentage yield, we would do 0.02407 divided by 0.04838, multiply this by 100. So what we're doing is actual divided by theoretical moles. That equals 49.8% as our percentage yield. Looking at the options we're given, the option we've calculated matches option A. So to get the mark for this question, we must write A in the answer box provided. A compound produces the carbon-13 NMR spectrum below. Which compound could have produced this spectrum? A. Propane, B. 2-methylbutane, C. 2-methylpropan-1-ol, or D, 2-methylpropan-2-ol. The first thing we need to notice is that the carbon-13 NMR has 3 peaks. Now we need to draw the compounds we've been given in the question. So we have propane, 2-methylbutane, 2-methylpropan-1-ol, and 2-methylpropan-2-ol. Now we can identify how many peaks we would predict in a carbon-13 NMR. So if we look at propane first, we would expect 1, 2 peaks on a carbon-13 NMR spectrum. So we can eliminate A as a possible answer because it doesn't match 3. Now looking at 2-methylbutane, well, we would expect 1, 2, 3, 4 peaks. So we can also eliminate this from our inquiries. Now looking at 2-methylpropan-1-ol, we would expect 1, 2, 3 peaks. So C, we're thinking, is our answer. But just to check, let's look at 2-methylpropan-2-ol. We would have 1, 2 peaks in a carbon-13 NMR spectrum. So we can also eliminate D. Now just to check, we notice that the peaks on the carbon-13 NMR for between 70 and 80 is that of a carbon-oxygen bond. And that means it's going to be an alcohol anyway, so the option could either be C or D from the list we're given, as they're both alcohols. Therefore, we've just confirmed in 2 ways that C is our answer to this question. To get the mark for this question, you must write C in the answer box provided. A carbonyl compound is reacted with NaBH4. Which compound or compounds could be formed? 1, 2-methylpentan-2-ol, 2, 2-methylpentan-1-ol, 3, 3-methylpentan-2-ol, A, 1, 2 and 3, B, only 1 and 2, C, only 2 and 3, or D, only 1. Firstly, a carbonyl group is any compound with a carbon double bond oxygen present, and NaBH4 is a reducing agent, so it would convert this carbonyl group into a COH group, so an alcohol group in other words. And looking at our compounds we've been given, they're all alcohols, so at a glance they're all possible. Now we need to look in more detail and draw the carbonyl compound that would react to form these organic products. So 2-methylpentan-2-ol, drawing this, we're going to replace the OH group with a carbon double bond oxygen. Now, looking at this compound, it's not possible because carbon must have 4 bonds, and this carbon at the moment has 5. So 1 cannot be an answer. So then we eliminate the options that include 1. So that would be A, B, and D. So that means we're going to write C in the answer box, but just to check, let's draw the carbonyl compounds of 2 and 3. So 2-methylpentan-1-ol, drawing this and replacing the OH group with a carbonyl group. This is possible because carbon would have 4 bonds. Now 3-methylpentan-2-ol, drawing this and replacing the OH group with a carbon double bond oxygen would look like this. Again, this is possible because carbon has 4 bonds, so 2 and 3 are correct. Therefore, to get the mark for this question, you must write C in the answer box provided. Which chemical or chemicals can react with phenol? 1, potassium hydroxide, 2, ethanol chloride, 3, nitric acid. A, 1, 2 and 3, B, only 1 and 2, C, only 2 and 3, or D, only 1. Drawing the reactions for these, we would have our phenol reacting with potassium hydroxide first. So reacting phenol with potassium hydroxide, we would produce a phenoxide ion, and then K plus would then bond and form a salt. So O minus K plus, and then we would have H2O if we were to balance this equation. Then phenol bonding or reacting with ethanoyl chloride, so drawing skeletally ethanoyl chloride here, we would form an ester group with the phenol attached. So we have our O or CO, then our C double bond O, and our R group. Balancing this equation, we would have HCl produced. Finally, phenol reacting with nitric acid. This is a mechanism called the nitration of phenol. So HNO3 reacting with phenol, we would nitrate the phenol, and we need dilute nitric acid for this to occur, unlike with benzene where you need concentrated nitric acid. If we were to balance this equation, we would have H2O produced. Therefore, all chemicals 1, 2 and 3 will react with phenol. So our answer is A. To get the mark for this question, you must write A in the answer box provided. The structure of a compound used to treat influenza is shown below. Which functional group or groups is or are in a molecule of the compound? 1. Ester. 2. Secondary amide. 3. Ketone. A. 1, 2 and 3. B. Only 1 and 2. C. Only 2 and 3. Or D. Only 1. So firstly, looking if there's an ester functional group present, we can identify here the ester group in the compound, which is our carbon-oxygen, carbon double bond oxygen group. So an ester group is present in this compound. Then looking for a secondary amide. Here we have a secondary amide because we have our amide group of our carbon double bond oxygen, our NH with R groups attached either side. So it's a secondary amide. Then looking for our ketone. In this compound there is no ketone group, so we can eliminate 3. A ketone would be a carbon doubly bonded to an oxygen with 2 R groups attached either side. And the R groups could not be a hydrogen or an OH group, because then if it was a hydrogen we would have an aldehyde, and if it was a OH we would have a carboxylic acid. So looking at our options, we're looking for 1 and 2, which is B. So to get the mark for this question, you must write B in the answer box provided. This question is about unsaturated aldehydes and alcohols. Part A. 3-methyl-but-2-NL, shown below, is used as food flavouring. 3-methyl-but-2-NL is reacted with hydrogen bromide, forming a mixture of 2 organic products. One of the organic products forms in a much greater quantity than the other organic product. Part 1. Outline the reaction mechanism for the formation of one of the organic products. Include curly arrows and relevant dipoles. This question is asking about electrophilic addition, so we're going to draw the mechanism for electrophilic addition of 3-methyl-but-2-NL. So if we start by drawing 3-methyl-but-2-NL and hydrogen bromide, we're then going to draw a negative dipole on the bromine and a positive dipole on the hydrogen.
The hydrogen has a delta positive sign as it's less electronegative than bromine. That's why we have a positive dipole on the hydrogen but a negative dipole on the bromine.
There's then going to be a curly arrow from the carbon-carbon double bond or electron density to the hydrogen, and from the hydrogen bromide bond to the bromine. A general rule with curly arrows is 1 in, 1 out. So we can see that there's a curly arrow into the hydrogen and then out of the hydrogen bromide bond to the bromine. Then we're going to form our intermediate. In the intermediate, the carbon-carbon double bond becomes a carbon-carbon single bond. The rest of the compound remains mostly the same, with the addition of a hydrogen. We can either add the hydrogen to the left or right hand side carbon of the carbon-carbon double bond. Here we're going to add it to the left hand side, and then the right hand side carbon becomes positively charged. Then we have our negatively charged bromine, and there's going to be a curly arrow from the centre of the lone pair on the bromine to the positive on the intermediate. It's essential that this curly arrow goes from the middle of the lone pair. Now we're going to form one of our products. We're going to draw our minor product, and that is because we've got a secondary carbocation intermediate. So drawing our minor product, we need to add the bromine onto the carbon where there was previously a positive charge. So this is our minor product. If we were to draw our major product, what would happen is we would have a tertiary carbocation intermediate, and the bromine and the hydrogen would switch places around our compound. So they're on different positions or different carbons in the products. So if we label this major, this is not essential in this question. However, if you do write it, you're showing the examiner you know exactly what the mechanism is, you know exactly why there's a major and a minor product, and it's just going to confirm that you know what you're talking about. To get the marks for this question, you get a mark for having the correct curly arrow from the carbon-carbon double bond to the hydrogen of hydrogen bromide. You get a mark for having the correct dipole on hydrogen bromide, or the correct dipoles, and the curly arrow breaking the hydrogen bromide bond. You get a mark for having the correct carbocation intermediate and the correct curly arrow on the intermediate. And finally, you get your fourth mark for having the correct product, depending on your carbocation intermediate. So here, the correct product is your minor product. Part 2. Explain why one of the organic products forms in a much greater quantity than the other organic product. The reason why one organic product forms in a much greater quantity than the other is something we've slightly touched upon in Part 1. We have a major and a minor product. The statement we need to write is that the reaction goes via the most stable carbocation intermediate, and this is touching upon Markovnikov's rule for electrophilic addition. And our minor product is a secondary carbocation intermediate, and our major is a tertiary. So we can see the higher we go in terms of being primary, secondary or tertiary, the more stable the carbocation intermediate. And this is what we need to write for this question. To get the marks for this question, you get your first mark for saying that the reaction goes via the most stable carbocation intermediate. You get your second mark for then noticing that you have a minor product with a secondary carbocation intermediate and a major product with a tertiary carbocation intermediate. Part B. Geraniol and citronellal, shown below, are isomers present in citronella oil used as insect repellent. Geraniol and citronellal are structural isomers of each other. They also show stereoisomerism. Part 1. Describe how the observations from a chemical test would distinguish between geraniol and citronellal. The test we're going to use in this question is Tollens reagent. Tollens reagent is a test that will distinguish between geraniol and citronellal, and it's a test for an aldehyde functional group. So it's going to produce a silver mirror with citronellal because there is an aldehyde group present in citronellal. Silver mirror is the positive result for Tollens reagent and its test. If we highlight the aldehyde group on citronellal, this just confirms what we already know. Highlighting functional groups is a really good way to then, when you look back at your paper, check your answers and know that you've got them correct. To get the marks for this question, you get a mark for saying Tollens reagent or getting the right chemical test, and a mark for having the correct positive result, so it's a silver mirror with citronellal. Part 2. What is the molecular formula of geraniol? If we start by identifying how many carbon atoms there are, on each peak of our skeletal diagram, I'm drawing a purple dot, and this signifies a carbon atom. Then we're going to work out how many hydrogens there are. But firstly, counting the number of carbons, we have 10 carbons present. So do C equals 10. Now using green for our hydrogen. On the carbon atoms as side chains on the end, we would have CH3. So we have 3 hydrogens. which I'm drawing in green. Now, carbon has to have 4 bonds. So on this carbon here, we already have 4 bonds because we have a double bond and 2 single bonds. But on this carbon, we have 3 bonds, so we would have 1 more hydrogen. Here, moving across, we have 2. Again, another 2. On this carbon, we have 4 again. It's a repeat of what we've seen earlier in geraniol. Then we have 1 and 2, and then 1 hydrogen in our OH group. Counting the number of hydrogens, we have 18. So we write H equals 18. That means our molecular formula will be C10H18O, the O coming from the OH group. To get the mark for this question, you must have the correct molecular formula of geraniol. Part 3. Explain why geraniol and citronellal are structural isomers of each other. The question is asking for a definition of a structural isomer. The definition for a structural isomer is that they have the same molecular formula and a different structural formulae. To get the mark for this question, you must write this statement: same molecular formula and different structural formulae. Part 4. Explain the term stereoisomerism. This question is asking us to define a stereoisomer. A stereoisomer has the same structural formula but a different spatial arrangement of atoms. So to get the mark for this question and explaining the term stereoisomerism, we need to write that stereoisomerism is when you have the same structural formula but different spatial arrangement of atoms. Part 5. The structures of geraniol and citronellal are repeated below with the carbon atoms numbered. Explain the types of stereoisomerism shown by geraniol and citronellal. In your answer, refer to the numbered carbon atoms in the structures above and draw diagrams clearly showing any stereoisomers. The first type of stereoisomerism we can talk about is in geraniol, where we have EZ isomerism around carbons number 2 and 3. So in the question, we're shown the E stereoisomer for geraniol. So we need to draw the Z stereoisomer. Drawing the Z isomer, we have most of the compound the same. However, around our carbon 2 and 3 double bond, we would have our group going down rather than going up, so that the highest priority groups are on the same side of the carbon-carbon double bond. So this is our Z isomer. Now we need to talk about the stereoisomers in citronellal. So now looking at the type of stereoisomerism present in citronellal, we have optical isomerism present in citronellal, and that is because we have a chiral carbon on carbon number 3. So we need to draw the 2 types of optical stereoisomers of citronellal. So now I've redrawn citronellal. I've drawn mirror images of each other because that's what optical isomerism is all about, non-superimposable images. Like your hands, they are mirror images of each other, but they cannot be superimposed. So if we were to show the optical isomerism, we're going to use wedges. So optical isomerism is around carbon number 3. So we're going to use a solid wedge leading to the aldehyde group on both sides of the mirror image, and then we're going to have a dotted wedge to show our hydrogen, which is one of our different R groups around carbon number 3, which makes it a chiral carbon. A chiral carbon is a carbon with 4 different functional groups attached. So carbon number 3 is a chiral carbon. So here we've now shown the optical isomerism or the stereoisomers of citronellal. To get the 4 marks for this question, You get your first mark for saying that there is EZ isomerism around geranyl and carbons number 2 and 3. You get your second mark for saying that there's optical isomerism and a chiral carbon on carbon number 3 in citronellal. You get your third mark for drawing the correct Z stereoisomer for geranyl, and you get your fourth mark for drawing the correct optical stereoisomers of citronellal. Both 3D structures being correct gets you this fourth and final mark.
This question is about amino acids RCHNH2COOH. Part A. Table 17.1 shows the R groups for 4 amino acids. Part 1. In the boxes, draw the organic products for the reactions of stearine shown below. Let's first look at the reaction between stearine and H+. Like with hydrolysis, the NH2 group turns into an NH3+ group. However, the rest of the molecule remains the same, so the carboxylic acid remains the same and the OH group remains there. Now let's look at the reaction between stearine and CH3-CHOH and sulfuric acid. So this is an esterification reaction, and we're going to form an ester link between our carboxylic acid group in stearine and the OH group in our reagent. The rest of the molecule will stay the same, and it's only this ester link we're going to form. When reacting stearine with CH3COCl, we're going to form an amide group, so our CH3CONH, that's our amide group, and we're also going to form an ester between our alcohol group on stearine and the CH3COCl group, or more accurately the carbonyl group in this acyl chloride. Now I'm just going to highlight the marking points of this question. So when reacting stearine with H+, and noticing that you form NH3+, this product gets you the mark. Having it fully correct will get you a mark. Then reacting stearine with CH3-CHOH and sulfuric acid, having your ester link in your product and the rest of the product correct gets you the mark, or 1 mark. Then, when reacting stearine with excess CH3COCl, having the correct amide group formed and ester group formed, gets you 2 marks. So this product will get you 2 marks towards the 4 marks of this question. Part 2. A student is provided with one of the 4 amino acids in table 17.1. A student carries out a titration with a standard solution of hydrochloric acid to identify the amino acid. The student's method is outlined below. 1. The student dissolves 5.766 grams of the amino acid in water and makes the solution up to 250.0 centimeters cubed in a volumetric flask. Part 2. The student titrates this solution with 25.0 centimeters cubed of 0.150 moles per decimeter cubed of hydrochloric acid. Then part 3. 21.30 centimeters cubed of the amino acid solution were required for complete neutralization of the hydrochloric acid. Determine which amino acid the student used. Firstly, we need to highlight the key pieces of information in this question. Our first key piece of information is the mass of the amino acid in water that we're going to use to make up the solution. Our second key piece of information is the volume that we make the solution up to in the volumetric flask. Thirdly, the volume and concentration of hydrochloric acid that we use. We're going to use this information to work out the moles of hydrochloric acid we use in this titration. And fourthly, the volume of the amino acid solution that's required for complete neutralization of the hydrochloric acid. Firstly, working out the moles of hydrochloric acid used. We're going to use the equation triangle of N divided by V times C. N standing for moles, V standing for volume, and C standing for concentration. So using the information in the question, we're going to do volume times concentration. Volume will be 25 times 10 to the negative 3 because we're converting centimeters cubed into decimeters cubed. Then we're going to multiply this by the concentration, 0.15 moles per decimeter cubed. That gives us 3.75 times 10 to the negative 3 moles of hydrochloric acid. Now we're going to use these moles to work out the moles of the amino acid. In order to do this, we need to take our moles, 3.75 times 10 to the negative 3, and multiply them by 250 divided by 21.3. This is factoring in the amount of amino acid solution we're required to use and dividing it by the total volume of the solution. Doing this gives us the moles of the amino acid. Those moles are 0.044 moles of amino acid. We're then going to use another equation triangle. We're going to use this equation triangle to work out the relative formula mass of the amino acid. This equation triangle is mass divided by moles times relative formula mass. So using the moles we've just calculated, we're going to do 5.766 divided by 0.044. The 5.766 is the mass of the amino acid we're using, and we dissolve in water to make up the solution. That gives us an RFM, or relative formula mass, of 131 for our amino acid. Using the general formula of an amino acid as RCHNH2COOH, which we get from part 1, we can then work out the R group using the relative formula mass. So we first need to do 131 minus 12 plus 1 plus 14 plus 2 plus 12 plus 16 times 2 plus 1. This is the relative formula mass of CHNH2COOH. That gives us 57. So then we need to match this 57 to the relative formula mass of one of the R groups. This matches the relative formula mass of the R group of leucine. So just to double check, that would be 12 plus 3 times 2 plus 12 plus 1 plus 12 plus 2. That equals 57. So that confirms that we're using leucine. So then we need to write as our answer that the amino acid is leucine. To get the marks for this question, you get 1 mark for working out the moles of hydrochloric acid, 1 mark for working out the moles of the amino acid, 1 mark for working out the relative formula mass of the amino acid, and then your final mark for identifying that the amino acid is leucine. Part B. The student is provided with another amino acid. The student attempts to identify the unknown amino acid using chromatography. The student obtains 2 TLC chromatograms of the unknown amino acid and the 4 amino acids in Table 17.1, using 2 different solvents, W and X. Part 1. What is the RF value of styrene, SER, in solvent W? When working out RF value, you need 2 values. You need the distance travelled by the solvent front and the distance travelled by your sample. So if we work out the distance travelled by the solvent front, that would be 2.6 centimetres. Then we're going to have the distance travelled by serine, or SER. So using our ruler, we can see that that is 0.9. Then that gives us a value of 0.35, which is what we write on the answer line for this question. To get the mark for this question, you must have a value or an RF value of between 0.33 and 0.35. Part 2. Analyse the chromatograms to identify the unknown amino acid. Explain your reasoning. Firstly, look at solvent W. We can see that the chromatogram for the unknown amino acid matches that of leucine and glycine. So this is our first line of explanation, that it matches leucine and glycine in solvent W. Then we need to look at solvent X. Looking at solvent X, we can see that the chromatogram for the unknown amino acid matches that of alanine and glycine. So this is our second line of explanation. So and matches alanine and glycine in solvent X. So that means our unknown amino acid is glycine. To get the marks for this question, you get your first mark for having the correct explanation and your second mark for correctly identifying the unknown amino acid, glycine. This question is about esters. Part A. The structure of ester A is shown below. Part 1. What is the systematic name of ester A? Esters are made from an alcohol and carboxylic acid. The alcohol part of the ester link is here. The alcohol we've used to make ester A is ethanol, so when naming ester A we would show this by using ethyl. Then we need to identify the carboxylic acid. So the carboxylic acid would be the rest of the ester A. So in this carboxylic acid, we would name it as 3-bromopropanoate. This is because we would classify the carboxylic acid group as the highest priority group, meaning that the bromine is on carbon number 3. So we would have carbon number 1, 2, and 3. To get the mark for part 1, you must have the full correct systematic name for ester A. Part 2. In the boxes, draw the organic products for the reactions of the functional groups in ester A shown below. Each reaction forms 2 organic products. Let's start by looking at the reaction between ester A and H+. When making an ester, you have an alcohol and a carboxylic acid alongside an acid catalyst, or H+. So when reacting an ester with H+, we're going to reverse this reaction and form our carboxylic acid and alcohol. So our carboxylic acid would be 3-bromopropanoic acid. So drawing this, we would have our carboxylic acid group and our bromine. Then our alcohol is ethanol, so we draw this skeletally with 2 carbons and our OH group. When reacting ester A with excess OH-, we are again going to form ethanol, and in order to do this we need to split our ester link. So splitting the ester link, we're then left with 3-bromopropanoic acid. However, with excess OH-, this is not going to be a carboxylic acid. We're going to have nucleophilic substitution occur, and we're going to have our OH instead of our bromine because of nucleophilic substitution. And then we're going to have a hydrogen removed from our carboxylic acid group and instead have an O- present. This would balance the charges of our reaction and ensure that it is the correct organic products for this reaction. To get the 5 marks for this question, you get a mark for each correct organic product and an extra mark for having the organic product with excess OH- correct, because you're reacting 2 parts of ester A with excess OH-, and so you get 2 marks for each part of ester A that you have correctly reacted with excess OH-. So that would be the carboxylic acid group and the bromine group. Part 3. Name the type of reactions of ester A shown in Part 2. The type of reactions shown in Part 2 are acid and base hydrolysis reactions. So for Part 3, the answer is hydrolysis. To get the mark for Part 3, you need to write hydrolysis on the answer lines provided. Part B. The protons in ester A are in 4 different environments, labelled 1 to 4 on the structure below. Complete the table to predict the proton NMR spectrum of ester A. Chemical shift values we can get from our data sheets that were given in the exam. So for proton environment 1, the chemical shift values are 3.0 to 4.3. For proton environment 2, the chemical shift values are 2.0 to 3.0. For proton environment 3, the chemical shift values are
3.0 to 4.3. And for proton environment 4, the chemical shift values are 0.5 to 1.9.
So here I've got a picture of the proton NMR spectrum from our data sheet that you get given in the exam. So if we look at our first proton environment, we have our CH2 group connected to a Br group. So then looking at the data sheet, we would be looking at our CH-Br group. And we can see that this falls between 3.0 and 4.3 on our proton NMR chemical shift values, which is what we've written in the table. So then if we look at proton environment number 2, we have our CH2 group connected to our Carbonyl group, or our C doubly bonded to an oxygen group. So that means we're going to be looking at our CH-C double bond O group, and that falls between 2.0 and 3.0 on our proton NMR chemical shift data sheet, which is what we've written in our table. We've written 2.0 to 3.0 for proton environment number 2. Looking at proton environment number 3, we have our CH2 group connected to an oxygen, so we're looking at our CHO group, and that is again 3.0 to 4.3, which is why it's the same chemical shift value as proton environment number 1, because looking at the data sheet, both CHBr and CHO fall within the same group on our chemical shift values for a proton NMR spectrum. Then looking at proton environment number 4, we have our CH3 group. So this would be our CHR group, and that falls between 0.5 and 1.9 on our proton NMR spectrum.
When working out splitting pattern, you need to look at the number of hydrogens involved in the proton environment next to the one you're looking at. So for proton environment 1, we need to look at proton environment 2 and the number of hydrogens involved. There are 2 hydrogens involved in proton environment number 2, so we need to add 1, and that would produce a triplet splitting pattern for proton environment 1. Then, looking at proton environment 2, we need to look at the proton environment next to proton environment number 2, and that is number 1. There are also 2 hydrogens involved in proton environment number 1, so adding 1 to 2 would produce a triplet splitting pattern. Then, looking at proton environment number 3, we need to look at proton environment number 4 because that's right next to it. There are 3 hydrogens involved in proton environment number 4, so for proton environment number 3, we would have a quartet splitting pattern because we're adding 1 to 3. And finally, looking at proton environment number 4, the next to proton environment number 3, there are 2 hydrogens involved, and so we're going to have a triplet splitting pattern produced for proton environment number 4. To get the marks for this question, you get 2 marks for having all 4 chemical shifts correct, and then you get 2 marks for having all 4 splitting patterns correct. Part C. Compound B is a structural isomer of ester A. Compound B reacts with aqueous sodium carbonate. The carbon-13 NMR spectrum of B has 4 peaks. Draw a possible structure for compound B. We're told we have a structural isomer of ester A and that compound B reacts with aqueous sodium carbonate. Using this information, we know that a structural isomer means we have to have the same molecular formula. The molecular formula of ester A is C5H9O2Br. Now we need to look for something that would react with aqueous sodium carbonate, and that would be a carboxylic acid. We also need to make sure that compound B would have 4 carbon-13 NMR peaks. So when we finish drawing compound B, we need to double check this fact and highlight where the carbon-13 NMR peaks would be found. So here I've drawn the possible structure for compound B, and analysing the carbon-13 peaks, we would have 1 peak for our CH3 groups, a second peak for our carbon between these CH3 groups, a third peak for our central carbon,
and a fourth peak for our carbon in the COOH or carboxylic acid group. However, there are some alternate structures or isomers that you could give and get a mark for this question. For example, we could have CCC with a carboxylic acid group at the end, and then we would have two CH3 groups in the middle carbon or the central carbon, two hydrogens on our left-hand side carbon with a bromine group. Now, if we identify the peaks in the carbon NMR spectrum, we would have 1, 2, 3, 4 peaks. So this is another possible structure for compound B. Similarly, we could have a third possible structure, and we would have a 4 carbon chain. So we would have C, 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 C. We would have a carboxylic acid group on our right-hand side carbon. We would then have a hydrogen and a bromine and a CH3 group and a hydrogen, because we would then make our left-hand side carbon a CH3 group. So when identifying the carbon environment peaks, we would have 1 repeated twice, 2, 3, 4, therefore making this another possible structure for compound B. To get the marks for this question, you get a mark for any correct possible structure for compound B. So any of these 3 structures would get you the mark.
Part D. A polyester is formed from 200 molecules of 4-hydroxybenzoic acid. What is the relative molecular mass, or MR, of the polyester? The first thing we need to do with this question is draw 4-hydroxybenzoic acid and work out its relative formula mass. So, drawing out 4-hydroxybenzoic acid, we would start with a benzene ring with a OH group attached to carbon number 4 and our carboxylic acid group attached to carbon number 1. Firstly, working out the relative molecular mass of 4-hydroxybenzoic acid, we need to count the number of carbons. There are 7 carbons present, so we would do 7 times 12. Then we need to add the number of oxygens. There are 3 oxygens, so we would do 3 times 16. Then we need to add the number of hydrogens. There are 1, 2, 3, 4, 5, 6 hydrogens present in 4-hydroxybenzoic acid, so we would need to add 6. That equals 138 grams per mole. Next, we need to note that we're forming 200 molecules. So we would do 138 multiplied by 200. That equals 27,600 grams per mole. But we're working out the relative molecular mass of the polyester. Polyesters undergo condensation polymerization, which means that they produce water. So we would need to do 27,600 minus 199 times 18. 18 is the relative molecular mass of water. That would be 2 plus 16. That would then equal 24,018 grams per mole, which is the relative molecular mass of the polyester. So we would write 24,018 on the answer line provided. To get the marks for this question, you get 1 mark for writing 27,600, and you get your second mark for writing 24,018. Part E. A student intends to synthesize ester C. Part 1. Plan a 2-stage synthesis to prepare 12.75 grams of ester C, starting from 2-methylpropanol, CH3 to CH-CHO. Assume the overall percentage yield of ester C from 2-methylpropanol is 40%. In your answer, include the mass of 2-methylpropanol required, reagents, conditions, and equations where appropriate. Purification details are not required. Firstly, we need to work out the mass of 2-methylpropanol required. In order to do this, we need to use the mass of ester C and the percentage yield. So we're first going to use the equation triangle of mass divided by moles times relative formula mass. And we're going to use this equation triangle to work out the moles of ester C. So that would be 12.75 divided by the relative formula mass of ester C, which is 12 times 5 plus 10 plus 16 times 2. And that equals 0.125 moles of ester C. Now we're going to use these moles to work out the moles of 2-methylpropanol. So that would be 0.125 multiplied by 100 divided by 40. This is where we use the percentage yield. That equals 0.3125 moles of 2-methylpropanol. Here I'm labelling the moles in order to show the examiner I really know what I'm calculating, and it's easier for them to then follow the investigation. We're then going to use these moles to work out the mass of 2-methylpropanol. So we're going to use the same equation triangle. We're going to do moles multiplied by relative formula mass. So we're going to do 0.3125 multiplied by 12 times 4 plus 8 plus 16. So how I've calculated this, 12 times 4, this means that there are 4 carbons in 2-methylpropanol that we're going to use, and then plus 8, which means that there's 8 hydrogens, plus 16, there's 1 oxygen. So then that's going to equal 22.50 grams of 2-methylpropanol. Again, I'm labelling the values I'm calculating in order for the examiner to know what I'm talking about. Now we need to write the relevant equations for 2-methylpropanol and how we're going to then form our carboxylic acid and our ester. So firstly, we're going to do our CH3 to CHCHO plus our oxidizing agent, which will be Cr2O72- or dichromate ions. They're going to be acidified, so we need to write H+, and we're going to reflux. Then we're going to produce our carboxylic acid. We're going to produce CH3 brackets 2 CHCOOH, and then we're going to write our equation with the carboxylic acid producing our ester. We're going to have CH3 brackets 2 CHCOOH plus CH3OH. So this is plus an alcohol. A carboxylic acid plus an alcohol produces an ester, but we need an acid catalyst and to conduct this under reflux. So we're then going to form our ester C, so that would be CH3 brackets 2 CHCOOCH3 plus H2O as our second product. Another piece of useful information when working out relative formula mass, so in our equation we've used relative formula mass of 2-methylpropanol. We could draw out 2-methylpropanol to help us keep track. So this would be CH with 2 CH3 groups attached either side, and then we would have our C double bond OH, or our aldehyde group. We're given the formula of 2-methylpropanol, but it does also help in organic questions such as this to draw out the structures and calculate the relative formula mass from there. To get the marks for this question, you must have correctly calculated the mass of 2-methylpropanol, and you must have planned the synthesis and include oxidation of aldehyde and the formation of ester C, with most of the reagents and conditions identified and the equations being mostly correct. This gets you the 6 marks for this question. Part 2. The mass spectrum of ester C is shown below. Suggest possible structures for the species responsible for peaks Y and Z in the mass spectrum. The first thing we need to do is identify the MZ value of peak Y and Z. So the MZ value of peak Y is 43, and the MZ value of peak Z is 71. So looking at ester C, we need something on ester C that would have a relative formula mass of 43 or 71.
Firstly, trying to identify the structure responsible for peak Y, we need to look at ester C and split ester C somewhere where we're going to be left with a structure with a relative formula mass of 43. So if we split just before the ester link, we're then given CH3 brackets 2CH+. Working out this relative formula mass, we would have 12 times 2 plus 3 times 2 plus 12 plus 1, and that equals 43. So this reassures us that this is the species responsible for peak Y. So we would then write CH3 brackets 2CH+ in the answer box for peak Y. Then looking for peak Z, we need something with a relative formula mass of 71. If we split midway through the ester link and we do the rest of the structure leading up, this would give us CH3 brackets 2 CHCO+. So working out the relative formula mass, we would have 12 times 2 plus 3 times 2 plus 12 plus 1 plus 12 plus 16. And that equals 71. Again, reassuring us that this is the correct species responsible for peak Z. So then we would write in the answer box CH3 brackets 2 CHCO+. To get the marks for this question, you get a mark for each correct species that you have identified.
This question is about benzene. Part A. Over time, the Kirkuli and delocalized models have been used to describe the bonding and structure of a benzene molecule. Part 1. Describe in terms of orbital overlap the similarities and differences between the bonding in the Kirkuli model and the delocalized model of benzene. First, we're going to draw a diagram for the delocalized model. So the delocalized model, we would begin drawing our diagram by drawing a hexagon. So like with benzene, we would draw a hexagon. However, then we need to draw our p orbitals. There would be a p orbital on each point of the hexagon. Then we would show our pi bonds by connecting the top p orbitals and making a hexagon, and then connecting the bottom p orbitals and making a hexagon. Finally, we need to annotate, so we need to label our pi bonds and label our p orbitals. So this is our diagram for our delocalized model. Now we're going to draw a diagram for Kirkuli's model. So Kirkuli's model, we would draw a hexagon, like with the delocalized model. However, we're then going to draw double bonds on alternating sides. So this is the diagram for Kirkuli's model. Now we need to talk about the differences between the two models. So if we begin with the differences with the Kirkuli's model compared to the delocalized model, Kirkuli's model has 3 pi bonds, which we can see as our double bonds on our diagram. But the delocalized model has a pi ring system. So this is what we would write as our differences, that the delocalized model has a pi ring system and so doesn't have 3 pi bonds, instead it's a ring system. If we want to show our similarities, we can label the Kirkuli model to show our pi bonds. To get the marks for this question, the way we've laid it out, we would get a mark for each diagram and a mark for our differences. Part 2. Experimental evidence led to the general acceptance of the delocalized model over the Kirkuli model. Describe 2 pieces of evidence to support the delocalized model of benzene.
For this question, we can lay it out as bullet points. Our first bullet point would be that all carbon-carbon single bond lengths are the same. This is a piece of evidence that supports the delocalized model of benzene. Our second piece of evidence is that benzene is less reactive than alkenes. For this question, you'd get a mark for each bullet point that we've laid out in this question. Part B. Benzene can be used as the starting material for the synthesis of compounds D and E, shown below. In the diagrams, C6H5 is a phenyl group. Compounds D and E can be converted into polymers. Part 1. Draw 2 repeat units of these polymers. Let's firstly look at the type of polymer we would form with compound D. We would form an addition polymer, and that means that the carbon-carbon double bond will become a carbon-carbon single bond. So if we were to draw this, we would have our carbon-carbon single bond, our hydrogens would remain the same, and then our phenyl group, our C6H5, would also remain there. We're asked in this question for 2 repeat units, so we would then draw this again, our carbon-carbon single bond, our hydrogens, and our phenyl group, C6H5. Then we need our longer bonds and brackets for this question to show that it's a polymer. We would also add an N to show that it could be repeated. Now looking at the type of polymer that we would form with compound E. We would form a condensation polymer and form amide bonds. So this means we're going to have NH at one end and then our CH3 phenyl group, C6H5, connected to a carbonyl group and then an NH. So here we've folded the polymer back onto itself and we've repeated it. So one side has just an NH on its own, and then we have our amide group that we're forming in the middle here. If we were to continue, we would then have our carbon with our CH3 group and our phenyl group, so C6H5, and we would then have a carbon double bond oxygen, our extended lines and brackets, and an N to show that it's been repeated. Part 2. State the type of polymer formed from compounds D and E. I've already talked about this in part 1, but just to reiterate, from compound D, the type of polymer we're going to form is an addition polymer, and the type of polymer we're going to form with compound E is a condensation polymer. With condensation polymerization, we form water. To get the marks for this question, you must have both types of polymer correct. Part 3. In the synthesis of compounds D and E, benzene is first reacted with ethanoyl chloride, CH3COCl, to form phenyl ethanone, shown below. The reaction takes place in the presence of aluminium chloride, AlCl3, which acts as a catalyst. In the mechanism for this reaction, ethanoyl chloride first reacts with aluminium chloride to form the CH3C plus double bond O cation. The CH3C plus double bond O cation behaves as an electrophile. Complete the mechanism for the reaction. Include equations to show the role of the AlCl3 catalyst, relevant curly arrows, and the structure of the intermediate. Let's firstly look at the key pieces of information in this question. The first key piece of information is that we're reacting with ethanoyl chloride, CH3COCl, and we're in the presence of aluminium chloride. This is our second key piece of information. Thirdly, that we're going to form our CH3C plus double bond O cation, which is our electrophile. So, with the formation of electrophile equation, we would write CH3COCl to show ethanoyl chloride, plus aluminium chloride, AlCl3, and then we would form our electrophile, CH3C plus double bond O, and AlCl4-. This is the formation of the electrophile equation. This mechanism is electrophilic substitution. So with electrophilic substitution, we would have a curly arrow from our pi ring to our electrophile with the positive charge, so in this case our C+. Then we would form an intermediate with a positive charge. The positive charge would be in our benzene ring, so we draw this a bit like a smiley face. And then we would have our COCH3 group and our H group. The H is reattracted back into the ring system, and then we would form our product and our H+. We use this H+ to regenerate our catalyst. So we would have H+ plus AlCl4-, because aluminium chloride is our catalyst, we need to form aluminium chloride, so AlCl3, and then we're left with hydrochloric acid, or HCl. For this question, you get a mark for having the correct equation for the formation of the electrophile, a mark for having the correct curly arrow from the benzene ring to your electrophile, a mark for having your correct intermediate, and a mark for having the correct curly arrow in your intermediate. And finally, you get a mark for having the correct equation for the regeneration of your catalyst. Part 4. Complete the flowchart for the synthesis of compounds D and E from phenylethanone. This question involves you learning your reaction map. The reaction map can be found on the website for the specification. So, firstly, with phenylethanone and NaBH4, this is nucleophilic addition. So that means we're going to get rid of our carbonyl group and it's going to be replaced with an OH group or an alcohol group. So drawing this product, we would have our benzene ring, and then we would have our carbon with an OH group, a hydrogen, and our CH3 group. What we've done with this arrow and compound D is converted our alcohol into an alkene. So the reagents that we require for this is H+ and heat. Then looking at the reaction with phenylethanone and NaCN aqueous and H+. Again, this is a nucleophilic addition reaction. So we're going to again form our benzene ring. This remains the same, but instead of having our carbonyl group, our C double bond O group, this is going to be replaced by our hydroxynitrile group. So that's our OH, our CN, and then we have our CH3 group remaining the same. Then looking at the reagents we require to go onto our next product, we would require NaBr and H+, because this is nucleophilic substitution. We are replacing our OH group with our Br group. Finally, we need a two-step synthesis to go and form compound E. So our first stage would be reacting with NH3 and CH3, CH2OH. What this is going to do is it's going to replace our bromine with an NH2 group. So drawing this, we would have our benzene ring attached to our carbon with our CH3 group, our CN group, and our NH2 group. Then reacting this with water or H2O, an acid catalyst or H+, and heat, that's going to form compound E. To get the marks for this question, you get a mark for having each product and each reagent and condition step correct. So in total there are 7. There are 3 products and there are 4 reagents and conditions. You get a mark for each. This question is about reaction mechanisms. Part A. Chemists use curly arrows in reaction mechanisms. Part 1. What does a curly arrow show in a reaction mechanism? The definition of a curly arrow is what we're asked in this question, and it's something you need to know for this specification. A curly arrow is the movement of an electron pair. So to get the mark for this question, you get a mark for saying movement of an electron pair. Part 2. Draw structures to show the products in the reaction mechanism below. So this reaction mechanism, we're going to produce H2O or water, and then that would leave us with the structure with a positive charge where we have our H2O. So to get the marks for this question, you get a mark for having the correct carbon skeleton and a mark for having the positive charge on the correct place on the carbon skeleton. Part 3. Use the mechanism in Part 2 to explain what is meant by heterolytic fission. For this question, you need to dissect heterolytic fission, and that means we're going to define heterolytic and then fission. Defining heterolytic, that would be when one atom receives both electrons. Then defining fission, fission is the breaking of a covalent bond. To get the 2 marks for this question, you get a mark for defining heterolytic, so saying that one atom receives both electrons, and a mark for defining fission, which is the breaking of a covalent bond. Part B. An incomplete reaction mechanism is shown below. Part 1. Complete the mechanism by adding curly arrows and any missing species. Before drawing any curly arrows, we need to look at the intermediate. So on the intermediate, we get rid of our carbon double bond oxygen, and it's replaced with a negative oxygen, and the OH minus has bonded to the carbon. So drawing curly arrows to reflect this, we would have a curly arrow from the centre of the lone pair on the OH to our carbon. This would bond it to the carbon. And then we would have a curly arrow from the carbon double bond oxygen to the oxygen, and this would produce our O minus charge. Then looking at our product, which will help with the curly arrows in our intermediate. In the product we have no Cl, so that means we're going to produce Cl minus. In order to do this, we would have a curly arrow from the carbon Cl bond to the Cl, and we've reformed our carbon double bond oxygen, so we need a curly arrow from the centre of the oxygen to the carbon, and that would reform our carbon double bond oxygen. For this question, you get a mark for the curly arrows in your reagent, so each curly arrow in your reagent gets a mark. Then you get a mark for the curly arrow in your intermediate going from the lone pair on the O minus to the carbon. And then you get 1 mark for having the curly arrow from the carbon to the chlorine and writing that this would produce Cl minus. Part 2. What is the role of OH minus in this mechanism? The role of OH minus, well, it acts as a nucleophile in this mechanism. So to get the mark for this part, you need to write nucleophile on the answer lines provided. Analysis of an unknown organic compound produces the following results. Elemental analysis by mass: carbon 73.17%, hydrogen 7.32%, oxygen 19.51%. Mass spectrum: molecular ion peak at MZ 164.0. Infrared spectrum shown below. Proton NMR in D2O is also shown. The numbers by the peaks are the relative peak areas. Use the results to suggest one possible structure for the unknown compound. Show all your reasoning. The first thing we're going to do is use the elemental analysis by mass to work out the empirical formula of our unknown organic compound. With empirical formula, what we need to do is take the percentages of each element and divide by their relative formula mass. So for carbon, that would be 73.17 divided by 12. For hydrogen, that would be 7.32 divided by 1. And for oxygen, that would be 19.51 divided by 16. Then we need to divide by the smallest. So for carbon, we would equal 6.0975. For hydrogen, we would equal 7.32. And for oxygen, we would equal 1.22. So the smallest is 1.22. So we need to do 6.0975 divided by 1.22. That equals 5. For hydrogen, we do 7.32 divided by 1.22, and that equals 6. And for oxygen, we do 1.22 divided by 1.22. That equals 1. So our empirical formula is C5H6O. Now we need to work out the molecular formula. We do this using our mass spectrum data. So firstly, we need to work out the relative formula mass of our empirical formula. So that would be 12 times 5 plus 6 plus 16, and that equals 82. But we're told that the molecular ion peak is at 164. So that would make our molecular formula twice our empirical formula. So we need to multiply by 2, and that would equal C10H12O2. Next, we need to analyse our infrared spectrometry data. So that would be stating the peaks and what they represent. So our first peak we're going to talk about is the peak at between 2,300 and 3,700 centimetres to the -1. That represents an OH group of a carboxylic acid. The peak we're talking about is here on our infrared spectrum. The second peak we need to discuss is the peak at about 1,720 centimetres to the -1, and that represents a C double bond O group. So that means that we have a carboxylic acid group present in our unknown organic compound. The peak for the carbon double bond oxygen is the smaller peak on the infrared spectrum here. Now we need to talk about our proton NMR and analyse the data that we're given here. So like with our infrared spectrum, we need to state the peaks and state what they mean. So our first peak we're going to talk about is at 1.6 ppm, and we need to discuss the splitting pattern. So the splitting pattern of this peak is a doublet splitting pattern. Our second peak is at 2.3 ppm, and its splitting pattern is a singlet splitting pattern. Then our third environment or peak is at 2.7 ppm, and its splitting pattern is a quartet splitting pattern. Finally, our fourth peak is at between 7.1 and 7.5 ppm, and it has a multiplet splitting pattern for this final peak. Using this data, we can identify the unknown organic compound. Our unknown organic compound will have a benzene ring with a CH3 group attached and a carbon with a carboxylic acid group present, a hydrogen and a CH3 group. This would give us the correct molecular formula and the correct infrared spectrum peaks. And now we're going to analyse the proton NMR peaks and where they would occur in this compound. So with this compound, we would have a singlet splitting pattern on our CH3 attached to the benzene ring because there are no hydrogens in the environment next door. Our quartet splitting pattern would be on our hydrogen of the central carbon and the side chain, and that is because there are 3 hydrogens involved in the environment next door, with our CH3 group attached to this part of the molecule. We would have a doublet splitting pattern because there's 1 hydrogen involved in the environment next door. And finally, our multiplet splitting patterns would occur on our benzene ring because they are in the right area, which is corresponding to our data sheet with the chemical shift values. The 7.1 to the 7.5 ppm values show an aromatic hydrogen.
The reason why we don't have a peak for the hydrogen in the carboxylic acid group is because we have a proton NMR spectrum with D2O. That means this OH group turns into an OD group, and so the peak would disappear on our proton NMR spectrum. To get the 6 marks for this question, you must have the correct structure drawn and you must have analysed most of the data in the question.